Good afternoon. I'm Chuck Tabor. I'm the Dean of the Graduate School, and I'm delighted to welcome you to another installment of the Provost Graduate Student Lecture Series. This is a series that we started 4 years ago. It's been a great success. It's become an incredibly competitive series where we receive more than twice as many nominations as we're able to accommodate in lectures. But it does really attest to the incredible quality of our graduate students. The purpose of the program is to give graduate students a chance to present their research to a broader audience, to talk to people not necessarily just from their department, but from other departments as well, and also to talk to faculty, staff, and sometimes undergraduate students from different departments. So we really hope to be able to foster communication across disciplines. I do want to mention in that light the two upcoming lectures. Some of you may be interested in coming to them, even though they're in very different disciplines. The next one is going to be on the 23rd, April 23rd at 3 here, and it's Eleanor Oppenheim of the music department who's going to be talking about the double bass. She's a performance musician. And then the one after that is from Geosciences, and that's on the 29th of this month, so we have two more still this month. And that's Kang Zhu from the Geosciences program is going to be talking about crystal structure prediction. Okay, so without further ado, I'm going to introduce Professor Yizhi Meng from Material Science, who's going to introduce today's speaker. Thank you.
Thank you, Charles. Okay. Well, good afternoon. Today it is my great pleasure to introduce to you Mr. Cheng Pan. I've known him in the department for the past 4 or 5 years. So he actually received his bachelor's in chemistry at USTC, the University of Science and Technology in China, in 2007. And he has been in material science and engineering since then. He is, besides, very nice guy and hard worker, he has been very proactive in outreach and education. He has volunteered countless summers, our high school program in the department, as well as many chemical and molecular engineering students. So he's been a TA with the department for a long time. Very enthusiastic educator. And today I'm proud to present Cheng Pan to you, and his talk is going to be enhancing the efficiency of bulk heterojunction solar cells via templated self-assembly. Okay.
Thank you for introducing me. Hello, everyone. So I'm Cheng Pan from Material Science and Engineering. So it's my great honor to be here to present my research to you. So my research focuses on the enhancing the efficiency of bulk heterojunction solar cell via the template self-assembly. So maybe many of you do not know what solar cell is. So basically, a solar cell is a device which can convert the energy of the light directly into the electricity by the photovoltaic effect. But what is photovoltaic effect? So I draw a very simple curve. That may be not very accurate, but I can somehow give you the idea what the photovoltaic effect is. So basically, when the semiconductor material absorbs the light, it will generate exciton. And by the effect of the electrical field, it will separate the exciton. Exciton is mainly, usually it's a pair of the electron and the hole. Electron has the negative charge and the hole has the positive charge. So if you build up an external circuit outside, so the electrons will go through one way and the holes will go through the other way. And in this way, you can generate electricity by the photovoltaic effect. So as you may know, the solar cell has been widely used in our normal life. It can be applied to the stuff as small as the calculator, or it's like the solar bag. You can charge your cell phone, you can charge MP3 wherever you are, if only there is sunlight. And scientists also apply the solar cell to the military uniform. So the soldiers can charge their devices wherever they are. And of course, solar cells have been widely used for the generating the electricity. They build up a large area of solar panels grid. And the right curve at the bottom show you what's the development for the solar power. So the cumulative installed solar power raised from 0.25 gigawatts to like 2.5 gigawatts in like just 10 years. So it's increased by a factor of 10, which means the solar power technology is developing very fast recent years. And this is a solar house that may come true in the future, which means you can have a solar panel on the roof, and the solar panel will absorb light in the daytime and generate electricity. And scientists can design some system to utilize this electricity to split water to hydrogen and oxygen. And the system can store the hydrogen safely in some place. So when there is no sunlight, the system can use the hydrogen for the electricity, for cooking, or even for the central heating. So in this, and also you can fill up your fuel cell car if you have one. So basically, you can build up a very independent electrical system in the future, and hopefully that may come true very soon. So here, because there are many different kinds of solar cells under development, like silicon solar cell, dye-sensitized solar cells, and other solar cells. And here we are going to focus on the organic solar cells. Why organic solar cells? Because first, the organic solar cells will have low manufacture cost. The reason for this is because the organic thin film on the substrate is like 1,000 times thinner than the silicon cells. And also the energy and the temperature that need to fabricate the organic solar cells is much lower than the silicon solar cells, which can reduce the cost by a factor of 10 to 20. The second advantage of organic solar cell is this solar cell can compatible with different substrates, which means if we spin our solar cell, organic solar cell on some soft substrate like PEO membrane, it can be very flexible. You can bend it to whichever angle you want. And the weight of the organic solar cell is very light. And also, because it can be deposited onto different substrates, you can produce the organic solar cell by different technology, like the solution process technology or printing. You can print the solar cell like you are printing paper. And also, you can use the raw-to-raw technology to produce solar cell. Oops. And the third advantage of organic solar cell is you can tailor the molecular properties of the organic solar cell. So you can easily change the functional group of the organic chain and in order to change the band gap and the light absorption of the cells. And also scientists can combine the organic molecules with the inorganic molecules to let the solar cell possess the properties of two kinds of solar cell, organic solar cell and inorganic solar cells, which can increase the efficiency. So that's basically three general advantages of organic solar cells. So there are maybe almost 50 years for the organic solar cell development. And the first generation of the organic solar cell is called single layer organic solar cell. There's just one layer which is made of the organic electronic material between the two electrodes. And under the effect of the electrical field between electrode 1 and electrode 2, they are trying to split the excitons generated by the absorption of light. However, because the electrical field is not strong enough to efficiently separate the excitons, so the quantum efficiency and the power conversion efficiency is very low compared to the silicon solar cell. So scientists developed another kind of solar cell after several years, which is called bilayer organic solar cells. So in this case, scientists divide the middle layer into two layers. One layer is electron donor layer, and the other one is the electron acceptor layer. So in this case, the excitons can be efficiently separated at the interface between the donor and acceptor layer. However, because the diffusion length of the exciton is usually like 10 nanometer, it's much less than the usual thickness of the layer, which is like 100 nanometer. So only a small fraction of the excitons can reach the interface between the acceptor and the donor layer, which means just a small amount of the excitons can be efficiently separated. So the quantum efficiency is still very low, and the power conversion efficiency is like less than 1%. So here I will introduce the bulk heterojunction solar cell, which we are doing research on. So this is the structure for state-of-art bulk heterojunction solar cell. Basically, it uses glass or some other substrates as the bottom layer. Then they coat an indium tin oxide as the electrode on top, and then they spin cast a p-dot PSS layer as the whole conductive material, and they spin cast an active layer on top. And finally, they have aluminum contact on top. So, so basically, the difference between the bulk heterojunction solar cell and the bilayer organic solar cell is scientists blend the electron donor and the electron acceptor material together. They mix them together as the one layer. So you can see there's different domains for in the active layer for the electron donor and for the electron acceptor domains. So in this case, there's much more interface area compared to the bilayer organic solar cell. And most of the excitons generated can reach the interface, then can be efficiently separated into the electrons and holes. So this can greatly enhance the efficiency of the solar cell. So that's BHJ solar cell. In order to let you further understand the principle of the BHJ solar cell, so I draw an energy band diagram here. So when the P3HT, which is the electron donor, P3HT absorbs the light, it will generate excitons. And at the interface of P3HT and the PCBM, the excitons will be separated. So because of the conduct band of PCBM is lower than conduct band of the P3HT, so the electrons can easily jump over to the to PCBM conduct band. And the holes will jump through the p-dot PSS back to the ITO electrode. And also you may notice that the work function of aluminum is like 4.3 eV. It's the same as the conduct band of the PCBM, which is electron acceptor, which means the electrons can easily, there's no band gap for the electrons jump from the PCBM to the aluminum. So the electrons can move freely. And in this way, the electricity is generated. But like a coin always has two sides, right? The BHJ solar cell also has like many disadvantages. Like it has a short lifetime. The absorption range is like very small. So, but here we are focusing on the surface morphology related disadvantage. As you can see, the structure within the active layer is very disordered, which means the donor or acceptor domains are isolated from the electrodes, and we call it dead ends, which means the electrons and or the holes cannot reach the electrodes on top or on the bottom. And then if they cannot reach the electrodes, they will recombine as exciton. And then, you know, by lowering the energy, they will back to the normal. So nothing happens here. So this is one problem. And also, even it finally finds some way to get to the electrode, but it, you know, you can imagine there's a very long conduction pathway, no matter for the electron or no matter for the hole. So this will cause the very high resistance for the electrons or for the holes to try to get to the electrode. And this phenomenon will significantly lower the power conversion efficiency. So in order to solve the problem here, so one group in Korea, they try to narrow imprint the electrodes into the active layer. They use the AAO mode, which is anodic aluminum oxide mode. They like insert the electrode into the active layer to shorten the conduction pathway between the electrons holes to the electrodes. So this can somehow enhance the efficiency of the solar cell. However, first of all, it's very time cost. You know, it takes a very long time to design the AAO mode to put that mode into the active layer. That's one problem. The other problem is the length of the electrodes that inserted into the active layer is very limited, which means the efficiency enhancement is also limited by this method. And the other group in Brookhaven National Lab, they designed the template with column holes on the surface. And they use this template to confine the organic semiconductors within the area that they designed. And this template-assisted confinement can help increase the hole mobility. However, the results show that the hole mobility is enhanced, but the electron mobility is limited. The reason for this is the aluminum will be very easily oxidized to aluminum oxide. And you know, aluminum oxide is a not very good conductive material. So, when the electrons are generated within the system, and but the electrons from the PCBM conduct band are trying to go to the work function of the aluminum oxide, but if those two band energy mismatched, so the electrons cannot move freely within the modes. So in this way, the electron mobility are highly limited. Okay, so we are considering because this idea is very great to confine the material, but we are considering whether we can build up the same structure without the template. So based on the previous references, when you mix like two different polymers together and anneal it, there will always be like phase separation on the surface. And by controlling the ratio between two polymers and controlling the annealing time, you can easily control the domain size on the surface. So here we are considering whether we can introduce a secondary polymer into the active layer to help generate the column structure. So this is the structure we want to build up. So basically the P3HD, which is the electron donor, will be made as columns dispersed in the secondary polymer phase. And the PCBM, which is the electron acceptor, will be segregated along the interface between the P3HT and the secondary polymer. So this structure, we think, it can help to improve the exciton dissociation efficiency because the interface area is very large compared to the bulk heterojunction or the other kind of solar cells. And also, when the PCBM are aligned along the interface between two polymers, then the electrons can easily go to the electrode because there's a very straight way for the electrons to go. They don't need to walk around within the active layer. So the conductive part is greatly shortened with this structure. So these are the challenges we are facing too. First, we need to produce structure with columnar morphology. And second, we need to try to combine the PCBM to the polymer-polymer interface. And third, we need to template the PCBM along the interface, as I said, to improve the electron hole or the hole conductivity to the electrodes. So since this idea is very new, it has never been done before. So before we really start the experiment, we need to do some theoretical calculation to help us predict whether this idea is possible or not. So we run some theoretical simulation with the help of Professor Dilip Gesapi and his group. they help us to run the molecular dynamics simulation. So here you can see 3 states of the system. The first one is the initial state. So it's just a P3HT and a PCBM and a secondary polymer. So the blue part is the P3HT phase, and the black spheres are PCBM nanoparticles. And the secondary polymer is not shown just for clarity. Okay, so at the initial state, you can see they are just mixed together. You cannot see any specific structure within the area. However, if you continue run the program, which in the experiment we will anneal the system on a certain temperature, you can see you can clearly see the column structure already formed within the active layer, and you can see PCBM like kind of segregate at the interface, but it doesn't matter. So if you continue running the program, which means you re-equilibrate the system, you will see a very interesting thing is the 2 columns from the second picture, they like merge together to form 1 column. So what this simulation can tell us, basically if we have experimentally choose a proper temperature and the proper annealing time, we can certainly achieve the column structure within the active layer. But one thing you need to keep in mind is here the delta is equal to 0.75. What's delta? Delta is the interaction between the P3HT and the secondary polymer. So when the delta value is less than 1, which means there is a repulsive interaction between the P3HT and the other polymer. So which means they don't like each other. So that's the important factor how the column structure can form. Okay, so now we know if the 2 polymers have repulsive interaction, they can form column structure. And then we need to know whether the PCBM will prefer to segregate at the interface between between the P3HT and the other polymer. So here we have 2 situations. We introduce another parameter, which is delta F. Delta F represents the interaction between the PCBM and the second polymer. So whenever the delta F is less than 1, it means there's a repulsive interaction between the PCBM and the other polymer. It's very similar to the previous one. Okay, so here the yellow spheres represent the PCBM at the second polymer phase, and the black spheres represent the PCBM at the interface. So when the delta F is equal to 1, what does that mean? It means there's no interaction between the P3HT and the other polymer. They like peacefully stay together. Okay, so in this case, you can see just almost half of the PCBM will be located in the secondary polymer phase, and half of the PCBM will stay at the interface between 2 polymers. However, if we change the value a little bit, which means there's a very little repulsive interaction between P3HT and the other polymer, you can see a significant difference is most of the PCBM will go to the interface between the P3HT and the other polymer. So these are the results from the theoretical simulation, and the results give us the confidence to continue our experiment. So we pick up a very common polymer, which is polystyrene. You must know what polystyrene is, like the plastic bottle you use for the water. Then most of them are made of like polystyrene. So we dissolve the polystyrene, P3HT, and PCBM together in the chlorobenzene with different ratio, and then we spin cast the solution on different substrates like the silicon or the TM grades or glass substrates, and then we characterize the morphology by different equipment to confirm the column structures really forms here. So the first equipment we use is a neutron reflectometer. Neutron reflectometer is a very powerful tool to detect the interdiffusion at the Z direction. And this is the image of the neutron reflectometer we use. It's located in National Institute of Standards and Technology, Center for Neutron Research. And the pin line is NG7. It's called neutron reflectometer. So we prepare the sample as this. So we first spin cast a very thin film, like 40 nanometer thick, on the surface of the silicon wafer. And then we put the silicon wafer, we immerse the silicon wafer into the water, and then we float another layer on top, on the surface of the water. Then we try to empty the water, so the thin film will be deposited onto the surface of the silicon. So in this way, that we can fabricate a bilayer on the surface of the silicon wafer. And here I need to mention we use deuterated polystyrene instead of the normal polystyrene because for the purpose of good contrast. And the sample will be dried in the vacuum oven at 50 degrees C for 6 hours and then annealed at 150 degrees C for different time. So here are our results. So first, we made a sample like this. So the P3HT layer is the bottom layer, and the deuterated polystyrene is the top layer. So the images at the left-hand side is the data from neutron scattering. The top one is the original data and the fitting data. And the bottom curve is the volume fraction in the z distance. So the dashed line is the volume fraction before annealing, and the solid line is the volume fraction after annealing. So basically, if there's just deuterated polystyrene and just P3HT, after 90 minutes of annealing, you can hardly see any interdiffusion between these two layers, which means there's very significant repulsive interaction between polystyrene and the P3HT. Otherwise, they will mix together. So if you still remember what I talked about from the theoretical simulation, so the repulsive interaction between P3HT and the second polymer is a key factor to generate the column structure. So here we prove there is indeed repulsive interaction between polystyrene and the P3HT, which makes it possible for us to generate column structure. Okay, so these are our second sample. So in this case, we have the blend film of deuterated polystyrene and the PCBM as the top layer, and we use the P3HT as the bottom layer. So after a certain time of annealing, we observed that most of the PCBM in the blend film will goes to the interface between the polystyrene and the P3HT. And if we continue annealing, some of the PCBM will goes into the P3HT phase, but no PCBM will goes back to the deuterated polystyrene phase. So this proves that there is repulsive interaction between the PCBM and the polystyrene. And if you remember, it is the key factor that we can segregate the PCBM at the interface of polystyrene and the P3HT. And we're also wondering if the PCBM is initially located in P3HT phase, where the PCBM goes back to the polystyrene phase. So we do this experiment. We use P3HT PCBM blend film as the bottom layer and use the deuterated polystyrene as the top layer. And we find after 90 minutes of annealing, no PCBM will goes back to the deuterated polystyrene phase, but there is a very thin layer of PCBM will aggregate at the interface between those two polymers, but most of PCBM will stay in the P3HT phase. Okay, so from the results of the neutron reflectivity, we find that we confirm that there is a repulsive interaction between polystyrene and the P3HT and between the PCBM and the polystyrene. So this gives us the possibility to create the column structure and segregate the PCBM along the interface. So then we make some real structure that is very close to the device, solar cell device. So we spin cast the blend film of P3HT and PCBM, or the blend film of P3HT, PCBM, and PS on the silicon wafer. And then we investigate the surface morphology by the atomic force microscopy. So the principle of the AFM is like the laser will be reflected on top of the tip to the directly and reflected directly to the sensor, and the sensor will transfer the electrical signal to the real image. And when the tip is scanning along the surface, because there's different altitude on the surface of the sample, so the tip will be deflected up and down. And in this way, the electrical signal will be varied, and the detector and the feedback system will give us the real surface morphology of our sample surface. Okay, so the images on the right-hand side are the images we get from the AFM. So the top one is the morphology for the sample without polystyrene. It's just P3HT and PCBM, and you can hardly see anything on the surface, which means the surface is very smooth. And if after we introduce the polystyrene into the system, you can see very significant phase separation on the surface, which means there are upper area, lower area, and they are like in very good order on the surface. And we are also very interested if what's the difference on the surface of morphology with or without the PCBM. So we did that, and we indeed find some difference. So the figure A is the surface morphology of sample without PCBM. And maybe you cannot see clearly. You can see the enlarge the picture on the right corner. You can see a very light ring at the boundary between two materials. So in the AFM image, the light part means the higher area, and the dark part means the lower area. So which means there's a raised ring around the boundary at the interface between two materials. And we think that's because P3HT doesn't like polystyrene, so the polystyrene will piled up at the boundary, and so which makes the boundary is higher than the left area. So that's how the raised ring formed here. And after we put some PCBM into the system, and we can see a significant difference here at the boundary. There's a depression at the boundary, which means the boundary is lower than the middle part or than the out part. So we think if we assume there's PCBM segregate at the interface, and because of the repulsive interaction between PCBM and the polystyrene, so the PCBM will exclude polystyrene into the outer phase. So in this way, the depression at the boundary will happen. But this is just an assumption. This is just kind of indirect evidence that PCBM will segregate at the interface. But in order to further confirm the segregation, we use the TEM to help us determine whether the PCBM are really segregated at the interface. So this is the TEM image for the sample without PCBM. That's just P3HT and the polystyrene. And you can focus on the boundary of the domain. You can see although there's some boundary there, but it's not that clear. However, after we introduce PCBM into the system and observed under the TEM, you can see a very significant dark line along the boundary, right? Like the A area. And if we enlarge the boundary and we measure the width of the boundary, it's about 16 nanometers. And this width is in agreement to the results we get from the neutron scattering. That's the interfacial width between the two layers. So, so in this way, we can somehow confirm this dark line is actually PCBM, and the other two phases, one is P3HT and the other one is polystyrene. And you may also notice that there's the ring is present when a small amount of polystyrene is trapped in the P3HT phase, you can see many small rings there inside that big domain. So it's also the dark ring around that small domain is actually PCBM, and inside is polystyrene that trapped in the P3HT, and the other phases are just P3HT. Okay, and if you take a look at the C area, you can see some, maybe not that clear, but still you can see some dark phases there. So actually there's still some PCBM trapped in the polystyrene phases, although they don't like each other, but you know, sometimes it doesn't up to him. So in this way, we confirm the segregation of PCBM at the interface between polystyrene and the P3HT. But how can we prove the column structure? So we need to take a look at the cross-section of the thin film. So we use TEM cross-section analysis. So the method is we spin cast our film on the silicon wafer, then we cut a small piece of the silicon wafer out, include the domain we want to take a look at. Then we deposit gold on the top just for good contrast, and then we insert that piece into the tube and cut a slice out. Then in this way, we can take a look at the cross-section of our film. So this is our results from the TEM cross-section. The top one is the sample without PCBM, and the bottom one is the sample with PCBM. And we just pick up one side of the domains, but the other side is actually the same as this one. So we find that regardless of the PCBM presence, there's always like column structure formed at the cross section. And you can also find that the boundary of for the sample with PCBM is much more clear than the sample without PCBM. And if you enlarge the picture, you can see many dark dots along the polymer interface and the interface of the silicon and the polymer, which means that could be the PCBM segregate at the polymer interface and also segregate at the interface between the silicon and the polymer. So by this TEM cross-section, we can confirm the column structure really formed by our method. So far, we already we have the theoretical simulation, and we have the neutron data, we have the AFM TEM data, which can confirm the aggregation of the PCBM along the interface. And we also use TEM cross-section to help us determine the column structure. So far, we already confirmed we really build up the structure we want, but next step is whether this structure really help to enhance the efficiency of the real solar cell device. So we fabricate some devices, and this work is mostly done in Brookhaven National Lab. So the left picture is the image of our real device that is ready for testing. You can see 5 big dots on the surface. That's aluminum electrodes. And there are also 2 silver electrodes at the edge. So the right image is the cross-section picture of our device. There's ITO glass, P.PSS layer, then our column structure made of P3HT, polystyrene, and PCBM, and then aluminum electrode. So we made our device as we first spin cast P.PSS layer on the glass substrate at 5,000 RPM for 45 seconds. Then we spin cast the active layer at about 700 RPM for 45 seconds. Then we deposit the aluminum electrodes at like 1 astron per second deposition speed until the thickness of the aluminum reach 100 nanometer. Then we anneal the whole system at 150 degrees C in the vacuum. So before we test our solar cell, we also take a look at the surface morphology by the AFM. And we can see the surface morphology is almost the same as the film is on the silicon wafer. And, and then we take a close look at some specific area, and we measure the lateral force of the area. Lateral force means it can reflect the hardness of the material. So the dark area means the harder material, and the light area means the softer material. So the figure C and figure D are the lateral force images for the specific area, which is within the red box. So we can see, maybe you cannot see clearly from here, but if actually the continuous area in figure D is darker than the certain domains on the surface, which means that area is harder than the left area. But by comparing the glass transition temperature, which is 100 degrees C for polystyrene and 50 degrees C for P3HT, so that dark area or the harder material must be polystyrene, and the softer area should be P3HT. So somehow we confirm that small domain should be P3HT, and that continuous area should be polystyrene. Then we measure the performance. We use the solar simulator from Oriole company, and this station consists of 150 watts of solar simulator and one AM 1.5G filter for the solar illumination. And we adjust the light intensity to 100 milliwatts per square centimeter. That's similar to the intensity from the sunlight. So here are our results. We can see the power conversion efficiency, which is PCE, is increased like 25% by introducing our column structure into the active layer. And by comparing the different parameters, VOC is the open circuit voltage, and the JSC is the short circuit current density, and the FF is the field factor. We can see there's not that much difference for the open circuit voltage and for the field factor, but we can see a significant enhancement for the short circuit current density, which means this column structure really improved the charge carrier transportation within the active layer. So this can enhance the current density of the solar cell and then enhance the efficiency. So our conclusion is like this. So first, we use the phase separation to create the columnar structure in the active layer of BHJ solar cell. And second, most of the PCBM are proven to segregate at the interface between the P3HT and the polystyrene phases. And we confirm that by TEM and the neutron scattering. And third, we can find a significant enhancement of the power conversion efficiency when we introduce this column structure into the active layer. That's mostly due to the enhanced electron and Hall transportation within the active layer. So at last, I would thank my advisor, Professor Miriam Rafaelovich, and I also thank Professor Dilip Gasapi and Dishu and Yosef Ott for their theoretical simulation. And I also thank Hongfei Li for device fabrication and the other help for the solar cell project. And I would also thank Dr. Yimei Zhu and Dr. Kim Kisling for the TEM characterization. And I would thank Dr. Chang Nan for the device fabrication. And for the neutron scattering, I would thank Dr. Bulent Akgan and Dr. Sushil Satija for their help of measuring the neutron reflectivity. And finally, I would thank our funding source, the Materials Research Science and Engineering Centers from National Science Foundation. Thank you for your attention.